Hi, today we're going to be covering Windbg and Plugx, and specifically using Windbg to defeat the Plugx anti-reverse engineering gadgets in a sample that was observed in the wild. This class is for individuals who want to expand their knowledge of Windbg and using Windbg to reverse engineer malware. This is not meant to be an authoritative class on Windbg, reverse engineering, or the Win32 API, or anything like that. If you're not up to speed on the topics presented in this class, visit opensecuritytraining.info for more information. So our goal today is going to be to defeat the anti-reverse engineering gadgets in Plugx and then to dump and decode the Plugx config. And we'll be using a script available online to decode the Plugx config. So as I had mentioned previously, this sample was observed in the wild during a state-sponsored APT engagement. It uses gpy.exe, which is the Google Pinion program. It sideloads debughelp.dll, which then loads up some shellcode that's on disk, and then finally it unpacks in memory, then executes svc hosts and MSI exec with a copy of itself injected into both of those executables. This particular version of Plugx also drops an additional executable that delinks the service name of the Plugx or delinks the Plugx service after startup, and then upon shutdown or reboot, it relinks it back into the list of services. This particular version of Plugx is type 1 and has a config size of hex 170C. So, as I had mentioned before, this one will load itself into svc host, MSI exec, and then it drops an additional executable. So if I go ahead and run it and open up Process Hacker, we'll see here that svc host is running with this executable and with this with MSI exec. And we can see there's an argument actually passed to this executable cp svcs, so we'll take a look at that a bit later, but we'll just need to remember that. So we'll go ahead and kill this. We're not going to break into it. We're going to debug it from the start because we want to defeat the shellcode, anti-reverse engineering gadgets, and then dump the config. So the first thing we need to do is examine these in IDA. So I'll go ahead and open them up in IDA, and we'll start with gpy.exe. So we can see here that we have gpy.exe, we have debughelp.dll, and then we have g.cn, which is the shellcode. This file description right here is the keylogger portion of Plugx. That's the output file, and this particular version, it's encrypted. So we'll go ahead and open up this. This is a regular executable, nothing special about it, besides it can be abused. So we already know that this particular Plugx drops debughelp.dll and abuses that. So what we'll do is we'll just sort here by library and find debughelp.dll. So here it is. Here's the library, and it calls any one of these three functions. Okay, so that's great. So we know it'll be one of these three functions: stack walk, sim get module base 64, and sim function table access 64. So we'll go ahead and open up debughelp.dll now. So first we'll check the exports that it has, so that's where these were, and if we notice that all three of the functions that are exported here all point to the same address, offset 12D3. So we'll go ahead and inspect that. So in this particular case, we notice that it's a really short function, and it just returns out here. Now what's interesting is we have a call to virtual protect, let's get module file name, but then we have this reference to this value right here. this function, and it's never called, but my suspicion is that it's just some return function pointer, return function abuse going on here, and that this is actually returned to. But regardless, we go into that function, we can see there's some additional get module file name, some string stuff, and then we have a reference to g.cn here. So that's pretty indicative that something bad's about to happen with that. Then we have a call to this function, which we'll loop back to, and then we have a call to virtual alloc with protection 40, which is read write execute. Then we have a call to memcopy, where the destination here is EAX after a call to virtual alloc, and this being 32-bit, we know that the value here, especially given that this is address 0, will be the memory address, and that's going to be the destination here, and then followed by a call to EAX. So we know for sure that this is going to be where it calls into the shellcode. So we can just go ahead and mark that now as a shellcode start. Okay, so now we know where the shellcode is going to start. It's going to start at this offset 12C4 from where it's loaded into memory. Okay, so that's fine. We don't really need to worry about that too much else. Oh, well, we'll take a look at this. We saw that g.cn name here, but we have no idea what's actually being copied in. Well, this function, we have create file, get file size, then we have a resolve virtual alloc with a call to load library and get proc address. Then I call to EAX, which after this call to get proc address would be the address of virtual alloc. So we go ahead and call virtual alloc, read the file, which this buffer here is EAX, which after this call to EAX, that value would be the new virtual alloc address space, because we can see the push 0 immediately before the call to EAX. And again, this is going to be read write execute. Then we have a call to read file, then a call to close handle. So we can be sure that g.cn is being read into that memory address space and then loaded up, copied into another memory address space, and then executed. So we'll go ahead and take a look at that. And since we made some changes there and made some markup, we'll save that file. So go ahead and go to g.cn. Now again, this is all 32-bit code. There's no 64-bit here. So again, we load in and IDA doesn't recognize any of it, so we'll click on the first byte and press C, and that'll create this jump instruction. Then we'll just go to the next byte and press C again. We get this message, do we want to directly convert to code? Yes. Okay, great. Okay, so now we have to do it one more time. Yeah, so right from the start in the shellcode, we could see that there was a lot of we already had to tell IDA to convert the data into code 3 times before we even get this thing correct. So we can see here, it looks like there's a short stub in this section, starting at offset 0, going all the way to this call to location 2. And then followed by some other code here, but this code is obviously not correct. This neg byte pointer, push CS, and then OR with this value. This is all incorrect. It's just it's obfuscated still. But if we go ahead and take a look at this little stub here real quick, it's pretty obvious what it does. So the first thing that we do is when we get in here, we jump to location 14, and there's a call to location 2 up here. So whenever we do a call, there's going to be a push onto the stack of the next address. And in this case, that's going to be location 19 here, which is this address. So we go up here to location 2, is the first thing is to pop whatever's off the top of the stack into ESI. Well, that's going to be the address here, whatever it is. So this call back up to here and then a pop is a clever trick to get the next address, or get this address regardless of what the memory address space is. Then what this does is it moves the value 35005 into ECX, and the reason it says offset byte here is because this memory address space is 0. So when it sees this, it interprets this 3500 as being address or hex 35005. It interprets it as being that address in here. That's why it's saying byte. When we rebase this, it will fix itself, and this will say just 35005 hex. So it puts that value into ECX, and then it adds that to this address 19, which is an ESI, and subtracts 1 from it, and then whatever that address is, it goes to memory there, and then subtracts hex B from the byte value, subtracts ECX by 1, and then jumps to location 8, which is just a loop here, and we can see the little loop on the side here, so we know that's what's going on. So this looks like it's decoding, but it's going from the end of the file down at the bottom to the start of the file up at the top. So that's fine. So at this point, there's nothing else we can really look at. There's no other code that we're going to find, because this value here, if we take a look at 35005, 3501E, that's going to be, those are about the same size, and to account for this little stub of code, hex 19, which is about hex 19 bytes away from each other, that would make sense. So now we'll go ahead and open up the executable in Windbg. Now, we don't need to do it in this case, but this debug child process is also, when we saw in Process Hacker, and as I described earlier, that this particular Plugx will inject itself into SVC host and MSI exec. If you click this box, debug child processes also, and let this run, each time Plugx, the parent process here, kicks off another thread, it will automatically break into it. But we won't need to use that in this particular case. Okay, so I've loaded up gpy.exe into Windbg, and it's broken in at this ntdll ntmap viewer section. I'm not sure why that actually is, but it doesn't matter. So the first thing that we're going to do is we're going to get into debug help and get to this interesting offset where the shellcode starts. Because the shellcode is starting from a virtual alloc address, we don't know the address yet. So what we're going to do is we're just going to go ahead and set a breakpoint on debug help at offset 12C4. And if we go ahead and we unassemble that data, or those bytes there, we'll see it's the same code. Call EAX, and then a push to push all these F's onto the stack, and then call sleep. So we're all set there. So if for whatever reason when you start up your Windbg and you're interested in a DLL and it's not loaded yet, you can use the BU command, which is for break unresolved, and that means basically you would put in the same command, debug help plus 12C4, but this would just tell Windbg that the library that you're interested in has not been loaded yet or resolved in Windbg speak, and when it is resolved, set a breakpoint at offset 12C4 from where it's loaded into memory. And so that's exactly what we want to do. And if we go here and hit BL, we'll see, okay, there we go. And it's interesting that with that, it actually goes directly to, it actually tells us what function that occurs in, and it's telling us it's in stack walk. Now we already know all the functions all point to the same address. So we've got that in there. We'll go ahead and hit G. Oh, and now we get loader do debugger break for whatever reason. Hit G again, and there we go. And now we'll see here we have the call to EAX. And in this case, it's at this address, same one there. So what we'll go ahead is we'll go into g.cn, which is the shell code, and we'll go ahead and rebase that. Whoops. Okay, so now that it's rebased, we can take a look and verify that what we're seeing in Windbg is what we see in IDA. And it is the same. We see the 8.19.2, 8.19.2 call. Okay, and we know this is a subtraction routine that goes from the end of the file to the next instruction, or to the next address after this instruction, and does a transform on it. So what we'll go ahead and do is, when we take a look at this, we know that this is the interesting address where the success is. So we want to actually breakpoint on that. Now, with breakpoints, software breakpoints, I should say, what those actually do is those actually patch the byte CC into memory where you tell it. So if we were to do a breakpoint here, it would actually patch in CC into memory. Now, in this case, we can't do that because a CC is not the original bytes. So when this subtraction routine goes over it, it's going to modify the byte CC instead of the original byte. So what we're going to have to use instead is a hardware breakpoint. And that's in Windbg called BA, break on access. And there's three different options: execute, read, write, and then several sizes: 1, 2, 4, 8 for byte, word, D word, and Q word. And then you put in the address that you're interested in. In our case, we're interested in execution breakpoint. And execution breakpoints in Windbg are always of size 1, and then the address that we're interested in. So we're actually interested in this address that we're going to jump to. So if we put this in, it will hold it will go into the processor and set a breakpoint there. And now with hardware breakpoints, there are 4 hardware breakpoints. And that's it. You can't have any more than 4 hardware breakpoints. And the way these work is by putting the address into a special register in the processor. And when the processor detects that address is in the instruction pointer, then it will break. So we'll go ahead and put that address in. And now if we hit G and go, we'll see, okay, we actually hit that breakpoint. If we were to double check, we would see our breakpoint 0 is at debug help offset 12C4, and then we're here at offset 19. So let's take a look at what's here. So we can just do EIP since that's where we know we're at. And here again we see another subtraction routine. Same type of thing. We know the success is here, so we're interested in that instruction. So we can set our breakpoint at that instruction, and then go ahead and hit go. And now we'll go ahead and unassemble EIP again, and we see yet again there's another one. Okay, so another subtraction routine. We know this jump right here is success, and we know that's the successful address. So we can do BAE1. And now mind you, this is our 3rd breakpoint in hardware, so we only have 1 more to use. So we'll go ahead and hit go, and breakpoint 3 hit. And now if we unassemble the instructions here, we'll see we actually have a call to some other, to something way far away, it looks like, because this is, we're at 3.8 for offset 4B, and then this is at 3B, so that's pretty far away. So let's take a look at what that is. I've already taken a look at this, so I already know it's hex 19 long, so I went ahead and put that in right here. So just to recap how we got here is that we broke into the call EAX, which we had determined from debug help was where it entered the Plugx shellcode. We looked at the first subtraction routine and went to the success address. We set a hardware breakpoint, executed to that address, then took a look at the code there, again, right here, UEIP, determined it was another subtraction routine, set a breakpoint at the success address, which we did right here, and then we went ahead and we executed to that point, unassembled again, so it was yet a 3rd one, went to that success address, set a hardware breakpoint, and now we found, once we went there, we found that the shellcode was going to do a call towards the end of the file to take a look at this, or to execute this function. So in this XOR routine, which is, here's the XOR right here, the XOR with 2 different operands, usually a dead giveaway for some sort of transform or encoding or decoding, something like that, along with a pop right at the beginning of the of this function, and we know that, as we saw previously, if we do a pop right after a call, it's going to get the next instruction, which is going to be this hex 50 offset here. So we know that the return is actually going to be to that address. So we can just go ahead and set the return right to that address directly and hit G. So I had meant to set the breakpoint to this address, 380050, but I accidentally did it to this return address. But if we hit T here and see where we go, we'll see that we definitely go back to that address. So that's fine. So again, we'll unassemble this code and take a look here. And we see again it's another subtraction routine. We see the sub here, the byte pointer, and then we have a jump to there. So we'll go ahead and clear out all our breakpoints, and then we'll go to this next one. We'll go to the next success, which is 380069. So now we see that there's a call. So we'll go ahead and just unassemble what's here and see whether this call goes, where this call is going to go. Alright, so it's definitely going to go towards the end. So I already knew it was going to be another XOR one. I unassembled for 19, and here we go. We see another XOR routine. Okay, so what's interesting here is if we were to dump this memory now, so what we'll do is here, we'll go ahead and dump this entire memory. So I don't remember exactly where this memory address space started, but since we rebased in IDA, we can just go ahead and get the address there, and it was at offset 380cc. So it looks like we've had a bunch of subtraction routines and a bunch of XOR routines. So let's take a look at this in IDA and see if we can make more sense of it, because it looks like a pattern is being established. So we'll write this to partial shellcode.bin. We know what the address is, and we know the length is actually going to be the same length as this, as what's listed here in IDA. So we'll go ahead and copy that in. Okay, great. So that's in there. So now we'll go ahead and we will open up our partial shellcode file. Okay, now we'll go ahead and we'll hit code on this and turn this all into code. So it'll look nice, and now we'll also check down at the end where our XOR routine was. So we can see here's our two XOR routines as it's displayed in IDA, and there's two of them here. And we see the same thing. The XOR DLCL, and we can see it down here, same thing, ink sub, ink sub. And now also, so we'll go back to the top real quick and take a look at these. And we can see here that we keep having a repeating pattern of these as well. We'll look at this 0B, and we'll see there's 1, 2, 3, 4, 5, so far 5 of these, all slapped right next to each other. Now we don't know what the actual amount here is. We just know that there's a whole bunch of these XOR routines in front of, or a whole bunch of subroutines at the start and a whole bunch of XOR routines at the end, but we have no idea how many. So what we need to do is figure it out. In this particular variant of Plugx, it's an arbitrary amount set by the builder, or set within the builder, I should say. So it could be 100, it could be 10, you know, who knows how many it is. So what we're going to do is we're going to try to figure that out. And it's actually not too difficult to do. So one of the first things we're going to do is we're going to use the evaluate command to get some offsets here. So the evaluate command again is question mark and the whatever address your, you know, whatever the two values are, and then your operation. So in this case is we want to see what the distance is between these two return addresses. So we can just look at this in IDA as well. It might be easier there. So we can see here our first return address for this, which would be the successful part of this, is at offset 3501B. So let's see how long this function is. Okay, so it's 53 bytes or hex 35 long. So what we can do is use our same thing like we were doing before, except doing it on the XOR side. Minus 35, because it's going from the end to the start. So we're going from a high address to a low address, so we're going to subtract. So we'll just take a look here and we'll hit go. So sometimes this will happen with hardware breakpoints, is that you'll set them and for whatever reason you'll get an error, and I'm not actually sure what causes this, but it really doesn't matter in this case because based on what we already know, it's very easy to get back to where we left off. We can see here that this was our breakpoint 0 was our last breakpoint hit, which is at this address. So it's at offset 69. We can just see here it's at offset 69. So what we can go ahead and do then is just restart the malware, and it'll pick up right from where we left off. We're going to use the same command that we did before, bu. We'll go ahead and hit run. Now, we know that we were at offset when we hit the 69. So if we set a hardware breakpoint again at our new base plus offset 69 and then hit go, we'll see we got right back to where we left off. Now the only other thing we have to do is go ahead and rebase our shellcode in IDA so that we can quickly match up what's going on. So in this case we'll go ahead and rebase this code, or our partial shellcode here I should say. We'll go ahead and rebase that, and now when we get to offset hex 69 we can see, okay, well here we are. It's going to call into this function, which is this thing here. So now what we want to do is we do want to see what's going on at this offset, at this return address here, but we want to see what's going on with it at. So let's clear out all our old breakpoints, and then we'll subtract 35 from that. We'll hit go, and we'll see here that we hit another return address. So just to double check, if we're to unassemble backwards from EIP 11 byte or hex 19 characters, we'll see here. What do we have here? Yeah, right here we got the pop because we're at the return, all this stuff, and here's the start of it right here, where we have the push these push values. And now there's some other changed values here, but it's no problem. These aren't correct. It looks like these are wrong with this push pop SS and then OR, so it looks like the subtraction routine hasn't run over this, but that's no problem, because again we just want to see what's going on 35 bytes away. Now since we know we're at the return address, we can just tell it EIP minus 35, and then we can hit go again, and we got to yet another return address. And if we were to do the same thing, it'd say okay, it's yet again another XOR routine. So now we can see these things are piling up right next to each other. Again, we still got to figure out a faster way to get through this rather than sit here and do it one at a time. So instead of individually doing these, what we're going to go ahead and do is we're actually going to try to send an offset in and see if we can find where this is going on. Now this is effective in this particular case because these functions are stacked up right next to each other. So if we use just regular x86 style addressing, we can think of this as base minus index, base minus offset times index. So we know we already went through 2 here. Well, how many are there? Are there 40? Are there 50? Are there 100? Well, when I did this, it was just a bit of guess and check, and luckily it didn't end up being too much. We know that there's a whole Plugx in here somewhere in this shellcode. And the shellcode's only about 214 kilobytes in total. So there can't be a lot of these routines in here. So what I started first with is I started with something like 50. See if there's 50 of them, and go ahead and hit enter, and it looks like something happened. Okay, cool. So with 50 of them, we get into this push EAX, and this actually broke into the code. So when I first did this, I actually didn't end up breaking into any code. Nothing happened. And the program quit on me. So we'll just take a look from here what we see here. We see here we have a push EAX and then a call to some offset and whatnot. So this is actually pretty interesting code. Let's see what else is going on here. Let's see. Well, you see there's a lot of interesting code going on, and it looks like it's a bunch of indirect calls and whatnot, and values being pushed onto the stack with moves and all that. So this is actually very, very interesting code. So in this particular case, I ended up getting lucky and actually chose an offset that broke directly into the shellcode that's going to be run. So what we're going to do in this case is we're just going to go ahead and clear the screen and restart here. And we're going to restart debugging. Normally you don't need to clear the screen, but I had done some other work in the course of recording this video and wanted to clear it out as to not confuse anybody. But we're going to go ahead and get back to where we left off. And then we'll go ahead and go into IDA and rebase our program again, or our shellcode. So that way we can get back to where we're supposed to be. And now what we're going to do is we're going to go directly to the XOR routine at the end, and we're going to stop there. Oh, well, it doesn't matter. It doesn't show the oh yeah, this is why I did it on the wrong one. It should be on this. Okay, and now we're already at the very end. We're going to grab this address here. We're going to set a hardware breakpoint there. We're going to hit go. We see we're there. So now what we're going to do is we're going to actually just skip directly to where the shellcode ends. The way I'd figured this out is just by walking in the offsets until it stopped crashing, and I wasn't in the shellcode. I was just before it. So basically, what I did was I had done some large offset like 100, and then went down to 50 or something like that, and then went down eventually, and I found that it was actually hex 21 bytes, or hex 21 rounds. What I had found is that there was hex 21 rounds of XOR routines before it actually entered into the shellcode. So that's what we're going to do here. We'll set it for 21. We'll hit G. We see we get to a return, and that return would be at whatever its DSP is at. So we'll use the POI command, and then we'll see here we have a call to the next instruction, so that's 721, then a pop, a subtract, a push this 170C, and then another call. So let's see what's in here. We have a push, and then we have another call, and then let's see what that is. Then we have a push, and then yet another call. So let's see what that is. And then we have a stack frame set up. So this is actually pretty interesting, that we have some different activity here than XOR and sub, and then we have a real stack frame set up. So what we're going to do is we're going to go ahead and write this memory out now. And then we'll use our starting address here. There's a starting address, and then the size is going to be 3501E. those bytes have been written, and then we'll go ahead and open those up in place of this shellcode. We'll go ahead and convert everything to code. There we go, and now it's all converted. It looks like we have a lot of functions in here and whatnot. So, well, let's see if it actually is. So, the first thing we'll do is we'll check where we were returning to. Oh, I didn't rebase this. I apologize. Okay, so we've gone ahead and rebased it, and now we can go to the address that we're interested in. There we go. And here we go. And so this is the argument, this is the start of the shellcode. So if we were to check this address again and just do more instructions, we can clearly see that this is the same shellcode. We have the IMUL here, we have an IMUL, we have the F segment offset 30. We have some other stuff. We have this jump down here, EAX plus EDX plus 8. This is all this. There is EDX plus EAX plus 8. The F segment offset 30. We have all that. So this is the same shellcode. So let's take a look at this shellcode and see what's going on with it. This up here in the top, especially this looks like it's walking the PEB to find something. And now I see some interesting stuff. G, E, T, P, R, O, C. So we have get proc address. We have load library listed right there. We have virtual alloc right there. We have virtual free listed right in here. We have exit thread listed there. NTDLL, RTL decompress buffer, mem copy. And then right after all that, we have the well-known Plugx algorithm right here. And then there's another copy of it right here. We have a whole bunch more shellcode. And then right here, this function returns. Function 3A14 returns. So we need to make some sense out of this shellcode before we dive into it any further. So it is pretty obvious what it does, and we'll start back up at the top of this function. So we see there's some stuff going on here. This is likely resolving some base addresses. But then we have this get proc address. So we see here get proc address. Okay. That's right, no calls or anything around there. It looks like it's getting it ready for something. And then we have the same type of thing with load library A, but then we have this call to variable 1C. So what it looks like here is, if it's moving EDX into var1C and doing these comparisons of all these values, it must be getting the address for get proc address here and resolving it manually by finding it in kernel 32. This is given away pretty much by the FS30 here, which I believe is the PEB. I'll have to double check on that, but I believe that's the PEB on 32-bit. And then all this walking through is walking the PE header and whatnot to find the import to find the in-memory in initialization order module list or some other module list in the PEB to get the address to get proc address. So let's put in get proc address here and see if that works. So we've got that in there. Okay, so load library A. So we have load library A gets put onto the stack, and then we see a call to get proc address, followed by taking the output of that and moving it to var90. So that's got to be load library without any question. So now we see here the same thing with virtual alloc, and our next call after virtual alloc is on the in memory is a call to get proc address, followed by EAX moved into there. So, and then a check to see whether it's equal to 0 or not. So this is probably virtual alloc. The next one we have virtual free, and it's the same thing. Get proc address EAX virtual free. And then we have the same thing here. Exit thread. Okay, and then we have NTDLL here, so this is going to be NTDLL. And then instead of get proc address, we have load library, so that makes sense, and that leads us to that should lead us to believe that everything else that we've looked at is correct so far. It seems to be matching up. RTL decompress buffer right after NTDLL gets pushed onto the stack, and then get proc address gets called, so that's definitely going to be correct. And then we have mem copy, same thing, that's an NTDLL, get proc address, so mem copy. And then right after all that happens, we see here there's going to be some decoding going on. Now, one thing that we did see is that there's this jump at the end of all these if the comparison to 0 is successful. So, and then we go down there, and that's the exit function. So we can just rename this exit. So now we can look, and there's a jump exit after all these in case that there was some sort of mistake. Even here, jump exit, call virtual alloc, and if there's a problem with it, exit. Do some additional work, do some more decrypting, and then another call to virtual alloc and exit. Then a call to RTL decompress buffer. If that fails, exit. Some more work. We see here compared to MZ. We see here compared to PE. So this is again looking for something. Then we have a call to virtual alloc with an executable memory space. We have the value plug being put on here. Again, with all these arguments being accessed. And we have another, we have a loop here of mem copy. Let's see here, widen this out a bit so we can see more. There we go, and see more of the loops. We have some other loop right in here that's doing something or other. I'm not really sure what's going on with that. Then we have a loop here to call load library, a call to get proc address, another call to get proc address, all wrapped in a loop. And then we get down here, we have a call right here, interestingly enough, to EDX. And so that's pretty interesting, as we have all this right before this call to EDX. Because when these things fail, they jump to exit, or this thing will loop back up. It'll have this call to EDX right after we have a loop to resolve a bunch of stuff. So if I had to guess, this would be the Plugx main, especially because it comes after a bunch of encryption or decryption and loading libraries. Because after this, the only calls are to virtual free and to return. So if Plugx doesn't run, and there's not really any calls here to anything that's bad or any other subroutines whatsoever. All these are calls to Windows functions. So it looks like that's where the Plugx main would be. Now, what we want to do is we actually want to take a look, though, at what's being passed this function real quick. And it's actually really easy with Windbg to see what's going on here. So once we get back up to the top of the function, what we'll do is we'll go ahead and set a breakpoint here, because we know this is already decrypted. And then what we'll do is we'll use the DDP command. So what DDP does is it is display DWord plus whatever the pointer value is. In this case, we're going to do ESP. So we're going to show all the DWords that start at ESP and then whatever they're pointing at. So we can see here that this is what's on top of this is what's on the stack after this thing was called. It might be a little easier to see it like this. So this is actually a bit easier. So we know there was a call. So that call will be to the return address. That will be the first thing on the stack is the return address. So if we're going to return right now, that's where we would go. The next thing here is we have a bunch of other arguments. Now some of these were already passed on, and if we copy this out, put it here. So if we go back up to the top here where we can take a look at what led up to calling into this function, we know that this is the return address, and now we're going to see this push of hex 170C. So it pushed onto the stack, and it looks like and that looks like it's right here, all the way down here, buried in the stack, because you know the thing that we pushed on first would be all the way buried in the stack towards the end of it. So here we go. That's the hex 170C. Now there's going to be a call, so we know the return instruction address is going to be pushed onto the stack, and that's correct. That's the 2D0752. Okay, that's fine. So now we unassembled what this thing called into, which was this address here. We come down here. Here it is. Here it is. So now what we see is there's going to be a push of 31BC3. And we see here, okay, there's a push of 31BC3. Now there's going to be a call to this address, and now that means this address is going to get pushed on here, and that's exactly what we see. Okay, great. And then when we unassemble that, we see a push of this value, whatever was in EAX, and if we remember, the last thing in EAX was this value right here, -5, which would be this, and then we see that. So we see the push of 341F8, and then we see the push of 2D071C. And that's these values are going to be important, these ones right here, and we'll show why in a few minutes. So okay, so we've got that done. We see that we're in the shellcode. We have some idea of what's going to go on with the shellcode, and we have an idea of where it's going to be run. So if we go down here and find that again, which is right here, we see here it's at this address. So if we go ahead to that address and just unassemble what's there, we'll just do one instruction. We see it's a call to EDX. So let's go ahead and run to that address, hit G, okay, and now we see it's going to be in here. We can unassemble again, and we see that there's some more interesting code with a call and a bunch of pushes and all that. But now what's even more interesting is we still want to get the Plugx config. And the way I found this was I actually ended up dumping this memory address space, this one right here, whatever that was in. When I opened it up at IDO, it's pretty obvious what I was looking at. So if I go ahead and just do this, and do bang on that, and then take a look at what's at the beginning of this memory address space, we see here we have the value gulp, or plug if it was forward. So if I do this now, if we do the same thing, and we take a look here, we see plug, which is the magic value for the Plugx config table, which is actually what we're looking at here. There was some research done by, I'll get the guys' names here, Takahiro, Haruyama, and Hiroshi Suzuki, which I have their Black Hat Asia talk linked at the bottom of the video. They actually went through and figured out what this Plugx config table looked like. And if I can get a photo of it here in the screen, I'll show you. Yeah, if we take a look at it here, we'll see that the Plugx table starts with the magic value plug right here. And then what it has is the pick pointer and the total payload length. So this is the pointer's some position independent code. This is the length of it. The encrypted real Plugx executable, its address, and its length. Then our encrypted config and its length. And at the beginning of this presentation, I said it was hex 170C size, and we see here that's what it is. And then the encrypted and decompressed Plugx entry point, which is right here. So if we were to take that value and unassemble it, we'll see that that value there is the same value that's in the call edx. And all these configuration values are the same one that were passed into Plugx at the beginning. So when it was passing all this in, and we see if we follow these, they're the exact same thing. The third one, here we go, 2DF, hex 170, and then this isn't the PIC address, it's not correct, but it doesn't matter. That's where it is. So that's what we have going on with this. Is actually when this program was starting, we had the whole Plugx config being passed in. The only thing we didn't know is where it would be the last value where the Plugx executable is going to start, but that's because Plugx itself didn't know yet because it hadn't run through all those virtual alloc calls to get that memory address space, and then do all its deobfuscation and copy it in and get ready to execute. So that's what it actually is. So now what we can do is we're really interested in this Plugx config. So now we already know where it is. So we can just write it out to disk. And it's at this address, and the length is listed right here. So pretty easy. So we go ahead and write that out. Now the Plugx config is encrypted. So what we're going to do is we're going to go ahead and decrypt it, and we're going to use a script that's available online. The link for that is in the YouTube description at the bottom of the video. So what we're going to do is run this Plugx decode.py. We're going to tell it what the file is, and we're going to tell it what the decoded file is. And you see here a lot of stuff popped out here. There's a lot of stuff that popped out, but here at the top, we see it did error out, but it was able to decrypt some stuff. So now what we'll do is we'll take that description, and we'll go ahead and run strings over it. And now when we see we run strings from it, we get the first 4 entries are some very long URLs that this malware was using, and then, or excuse me, not URLs, domains, and then some interesting information about what it's masquerading as. In this case, it's masquerading as the Citrix Print Manager service and the Citrix Advanced Universal Printing Architecture message here. There's some other value down here, the DRS, I'm not sure what this is. Whatever, it's being interpreted as a string, but it's unimportant for right now. So we were able to dump that. Now the other interesting thing is because we know where this executable, or we know where this unpacked executable is. Well, we already know what the address space is. So what we can do is we can write that to disk, and we know what length it is already because the length is that second argument there. Oops. Or that second value. And then we can take that and open it up directly in IDA. Go ahead and save what we have here. And now we would just need to rebase it as normal and and then move to that address that we're interested in. So we'll rebase our program, which is right there. And then we'll go ahead and go into the address where it started, and now we see where we're at, and we can go ahead and basically start reversing Plugx however we see fit, whatever we want to do or whatever we want to take a look at. We can go ahead and reverse this. So that's the whole thing. And now in addition to that, the other thing we can do is we can go ahead and run strings on it. And now if we were to just open up that file in Notepad++, and we'll just take a look for this program, we can see that there's 5 different mentions of this program cannot be run in DOS mode in here, with some interesting strings and whatnot. We have this especially interesting one, King of Phantom 308 2014 0826, and we have that there. So we can see here that there's a lot going on, and then in addition to any sort of HTTP stuff, here we can see a bunch of different things for HTTP, including what might be sent across. Looks like this thing's proxy aware. What a possible URI might be, any HTTP headers, so we can go ahead and look for this in our network traffic or whatnot, if we have that capability. But that's really what I wanted to show today. Now, this is all well and good, and it seemed to have taken a bit of time, but there's actually a much faster way to get around this. If we wanted to, and we had done our dynamic analysis beforehand, based on what we know from watching this thing just in Process Hacker, we know that it's going to start SVC host and MSI exec, and it's likely going to use create process to do that because it's going to start a whole new process. So instead of going through all this, and you can definitely verify in Procmon this thing will start a process using create process. We can just go ahead and breakpoint on create process. In this case, use create process W. We can go ahead and breakpoint on that and let this thing run, and we'll see it eventually hits. And now we're going to use the command called KB, which shows the call stack, and it shows us how we got here. And if we take a look at this, to get into the kernel 32 create process W, it was called from this address. And then this address was to get into this address, it was actually called from here because it's a different module. You see these are all different modules that it calls into. So anyway, we know that once we're done with create process, we're going back here to this return address, and these were some of the arguments that were passed in, and this is what the stack pointer base address was for that function when it goes back. But if we just take a look at that address, we'll see that it's at this memory segment, and then if we just do db, we'll see that we have gulp, and we could just go ahead and dump this address. So for future versions of Plugx, after you do a bit of dynamic analysis on them and see when they kick off their, finally kick their payload off, simply breakpointing at the create process W, showing the call stack and verifying, okay, well, where did we get into create process from? Because once it creates the SVC host process, it's going to inject its code and then start executing in there. So we know this is probably a pretty good place to stop or to break and then check. We take a look at this return address and find out what its memory segment is, and we even see it's the same size as the previous one, even though this is a completely different or another instantiation of this malware. We can see that it's the same size, and we have the address at the beginning here. And if we were to DD that, we would see that hex 170C value expected, and we have the A1C, which is the correct offset, and we have all the other values here. So really, if you want to do this quick for Plugx, it just takes three commands. You break into create process W, You use KB to find out what the return address is to create process W is, and then you find out the whole address space. I'm sorry, 4 commands, and then you can write it all out to disk if you want. So that's how that works. So really, this can be done much quicker than going through manually and checking all that out and working through those XOR and subtraction routines. So thank you for watching the video.